Here we are going to do three examples at once because they tend to have the same relationship, so it's best to show them all at the same time. But before we do that, I just want to point out this symbol right here. This symbol is pronounced as Aleph Null, and this symbol right here is not a Greek symbol. It's an ancient Hebrew or Semitic type of hieroglyph. And then this part right here, this is our null part. That's just a subscript of a zero, and zero null means zero. So this is pronounced Aleph Null. And Aleph Null is a symbol that we use to show that a set is countably infinite. And what is countably infinite? That means all the elements in the set, you can count them, but the counting goes on forever and ever. So how do you show the cardinal number of a set that counts on forever and ever? Well, that's why we use Aleph Null. That's where Aleph Null comes in. Now, the way to determine whether a set is countably infinite, goes on and on and on and on, is we're going to use the natural numbers, also known as the counting numbers, to help us do that. So the first thing I'm going to do is I'm just going to list all the natural numbers here. So here's n, that stands for the natural numbers, which are the counting numbers. And what I do is I go ahead and I start listing them. 1, 2, this is like the roster method. Now this is a specific pattern that the counting numbers have. 1, 2, 3, 4, 5, 6, and of course the ellipses means that this pattern continues. But I also want to show this in a general term. I don't want to have to list it in a specific pattern. I want to do it in a general term. So the general term for that would be the letter n, which stands for number, or natural number, or counting number. And then, of course, I want to show that this natural number consists of the same pattern that we've established here. So this is also going to go on. So now here is a set that represents the counting numbers, the natural numbers. In this set, we showed that it has a specific pattern like this, and then we also have a general pattern that looks like that. Now, what we need to do is we have to take a set and show that it can be paired up with each element of the natural numbers, and that's known as one-to-one correspondence. I'm just going to write it up here. So that means that every element of a set can be paired up with every element of the counting numbers of the natural numbers. So now what I'm going to do, it says verify that set W of whole numbers has the cardinal number of Aleph Null. So now what I'm going to do is I'm going to list out all the whole numbers. Now whole numbers are the counting numbers plus 0, or in other words, the counting numbers which also include the origin. That's what 0 is. So I'm going to do 0, 1, 2, 3, 4, 5, and as we can see that this pattern continues. But now what I need to do, similar to what I did for the natural numbers, is I have to represent this pattern in a general term, and I'm going to use the natural numbers to help me do that. And what that's going to be, this is going to be n minus 1. And what that means, since n is an element of the natural numbers, if we go to the smallest natural number, that's 1, and we slug it in over here, 1 minus 1 is 0. Go to the next natural number, 2. 2 minus 1 is 1. Go to the next natural number, 3. 3 minus 1 is 2. So we can see if this pattern continues, then we can see that every whole number can be paired up, or in other words, what we say one-to-one correspondence, with the natural numbers. So what does that mean? That means the cardinal number of the natural, or the whole numbers, I should say, is equal to Aleph Null. And this is how I write Aleph Null. I just kind of do it like that. And there we go. Now we're going to do the same thing for the other example here. It says verify that set E of even numbers has the cardinal number Aleph Null. So I'm going to list the set of even numbers. 2, 4, 6, 8, 10, 12, and of course this pattern would continue. Again, this is a specific pattern. I want to have a general pattern also in here. So what makes an even number an even number? Well, an even number has a factor of 2 in it. So I'm going to list this as 2n. So if n, the smallest natural number is 1, 2 times 1 is 2. The next natural number, that's 2. 2 times 2 is 4. The next natural number is 3. 2 times 3 is 6. So it seems as though this pattern continues. So here we go. So we've shown that every element of the even set of numbers can be paired up with every element of the natural numbers or the counting numbers. In other words, we've shown that it has one-to-one correspondence. Since we were able to show that, then the cardinal number for the even numbers is Aleph null. Don't forget, Aleph null means that the set is countably infinite. Now, as long as we did the even numbers, we might as well do the odd numbers too. So I'll list that as O. We first set a pattern for our odd numbers. 1, 3, 5, 7, 9, 11, ... Now I have to be able to figure out a general term. And think of it this way. If n is equal to 1, then 2n, which represents our even numbers, is equal to 2. So how can we get this to equal to 1? Well, I guess we can say if n is equal to 1, then 2n minus 1 is equal to 1. So I'm going to try that. 2n minus 1. Our smallest counting number is 1. Always start with the smallest counting number. You shouldn't start anywhere in the middle of the pack, because if it works for the first or second counting number, then it's going to work for the rest. So 2 times 1 is 2 minus 1 is 1. We'll use 2. 2 times 2 is 4 minus 1. That's 3. We'll use 3. 2 times 3 is 6 minus 1. There's 5. So it seems as though we have established a general pattern. I'll go ahead and list it. And we're done. So we could also say that the cardinal number of odd numbers is also Aleph null. And finally, for the last one here, it says verify the set Z of integers has the cardinal number of Aleph null. Now you could think of integers as the whole numbers and their opposites, meaning their negatives. Don't forget 0 is the origin, so it's not going to have a negative. So I'm going to put in the integers here. Now, since we're doing counting usually just kind of goes in one direction. I'm going to list all the integers only going in one direction. So I'm going to start off with 0, 1, -1, 2, -2, 3, -3, 4, and I think I've got a pattern going here. We could see 0, 1, -1, 2, -2, 3, -3, 4. You can guess -4, 5, -5, 6, and on and on and on. So now that I've established a specific pattern, again, I want to put in a general pattern. Now we can see up here, n minus 1 will give us our 0. So maybe I'll use n minus 1. So when n is 1, the smallest counting number, 1 minus 1 is 0. When I use 2, 2 minus 1 is 1. So far so good. When I use 3, 3 minus 1 is 2. So I skipped over the -1 here. When I use 4, 4 minus 1 is 3. So if I use n minus 1, I'm going to miss out on all my negatives here. So rather than use n minus 1, how about if I do this? How about 1 minus n? So when n is 1, 1 minus 1, that's 0. When n is 2, 1 minus 2 is negative 1. When n is 3, 1 minus 3 is negative 2. So this skips over all the positive numbers. But it does give me 0. So it gives me these numbers here. It gives me 0. It gives me 1. It gives me 2. It gives, I should say, negative 2, negative 3. So it seems as though it gives me every other element according to our specific pattern here. So no matter what I do, there is no general term that I can write down that's going to cover all of these. So I have to put in another one. And of course, that will cover 1, 2, 3, 4. And what is 1, 2, 3, 4? Well, that's just the natural numbers. So we'll check it. 1, 1 minus 1, that's 0, and then 1, there's 1. When we use 2, 1 minus 2, that's negative 1, and 2, that's 2. When I use 3, 1 minus 3, it's negative 2, and then 3 is 3. So I think we've established a general pattern here for our integers. However, when I go ahead and want to pair each one of these elements up with the elements of the natural numbers to see if there is one-to-one correspondence, to see if the cardinal number of the integers is Aleph null, I'm going to pair up 1 with 0, 2 with 1, 3 with negative 1, 4 with 2, and on and on and on. Then when I come to our ellipses here, I could pair this up with our ellipses here. But then when I get to this general term here, it could only point to one of the other general terms. Chances are it's probably going to point maybe to this one. But what do we know about the natural numbers, the counting numbers? Well, we know that they're made up of even numbers, 2, 4, 6, 8, 10, 12, on, and they're also made up of odd numbers, 1, 3, 5, 7, 9, 11, and on and on and on. So why don't I use that rather than just using this symbol here, n, to define my elements in my natural numbers? I could also use these, 2n and 2n minus 1. So maybe that's what I'll do. I haven't disrupted what the elements are of the natural numbers, so why don't I use that too? So our natural numbers could also be defined as 1, 2, 3, 4, 5, 6, 7, 8. We've established a pattern here, a specific pattern. Now let's generalize it. We'll do 2n minus 1, and then 2n. So we can see that when n is 1, 2n minus 1, that's 2 minus 1, that's 1. 2 times 1, that's 2. Slug it in up here. 1 minus 1, that's 0. 1 right here, slug it in right here. When n is 2, 2 times 2 is 4. Minus 1, that's 3. 2 times 2 is 4. Slug it in over here. 1 minus 2, that's negative 1. And then 2. So it seems as though every integer can be paired up or shown to have one-to-one correspondence with every counting number or natural number. So then the cardinal number of elements of the integers, that's equal to Aleph null. So the key is to use the set of elements of the natural numbers, which is the counting numbers, to help develop a general term that will define some other set.